Okay, so this is broadly what you have in your information, but I've changed it a bit since then, so you won't be able to follow it exactly. Anyway, good morning, everybody. Thank you very much for coming to this session. And as Laura said, if I had a pointer, it would be good if this was very interactive, because I have no idea what your background is and how much of this you know already and how much is really new to you. So please stop me if you're not following something.
We usually use this
old-fashioned
pointer,
yeah.
It's okay?
Could maybe Laura bring me another one? Because could you ask if she's got a laser? Laura, I think she was going to get one. Yeah. Oh, do you have the laser?
Yeah.
Yeah. So you all did a practical yesterday where you released glycans from IgG, that's right. And how far have you got? Did you put the label on?
Not yet.
Not yet, right, so you just did the release. So some of the point of doing this analysis is obviously to satisfy the regulators. And the regulatory agencies, like this is EMA, this is the European agency. Most of the agencies have signed up to what's called harmonisation policy. So they're trying to make the requirements for drugs to be regulated the same across the world, because it becomes very difficult if a drug is approved in one country but not approved in another country. So most of the agencies, at least for IgG, are on the same page. So they are asking for this kind of information. You have to describe the carbohydrate content, so the neutral sugars, the amino sugars, the sialic acids, for example, and also the structure of the carbohydrate chains, so not just a monosaccharide analysis, because believe it or not, a lot of legacy products, that's their glycoanalytics, just a monosaccharide analysis. You have to be able to give the oligosaccharide pattern, which they call the antennary profile. You have to look at the glycosylation sites, and then more and more they're asking you to do specific site analysis and site occupancy studies. And so if you're looking towards IgG, they're looking for you to show the level of manosylation, which really shouldn't be there. If the bioprocess is going properly, they're asking for galactosylation, fucosylation, sialation, and so on. And then they're asking for the distribution of these sugars, G1, G0, that's no galactose on the antennae, G1, one galactose on either of the antennae, and G2, that's when you have two galactoses. And then they want to know, of course, higher order structure, various pieces of information about the protein. So that is one reason for doing glycan analysis, but of course there are all sorts of other reasons why you might do glycan analysis. So there are different levels that you can undertake. So before you ever start a glycan analysis, you need to know what it is you need to know, because doing a complete glycan analysis may be very important for some things, but it may actually not be relevant to other things. So before you even decide which technologies to use and what information you're going to report, you need to understand what it is you need to know. Do you just want to profile? Do you just want to look at all the EPOs on the market and see how different the glycosylation profiles are from each other? In that case, you don't want a detailed analysis, you just want a quick release, you want a label or something, you want a high resolution technology, and you just want to be able to see just a big picture of how things are different. If you're doing at-line analysis, you might only want to profile because you know the analysis so well, you just want to see whether various sugars are going up and down as a result of the length of time of the process. And these can be any kinds of technologies. They could be LC, they could be mass spec, they could be CE. There are a whole range of separations technologies that you can choose from. And then you might just want to know about single features. You might just want to know, are there any antigenic epitopes? And so you would just, thank you very much, that's lovely. You would just maybe have an assay just to look for those antigenic epitopes. Or you may be looking for critical quality attributes. So if you're looking at EPO, you might just want to know how much is my molecule silated. And then you might want a bit more detail. You might want to characterize your glycans, to look at classes of glycans. So divide them into those which have one charge, or one or two charges, or three or four. You might want to quantify the numbers of the antennae. How much is biantennary, how much is how much is tetraantennary. And if you're doing a basic research project, of course, you definitely need to know details of monosaccharide sequence, linkage, anomoricity. And in order to determine that, you need a multifaceted approach, because no one way of doing glycan analysis will give you all the information that you need. And there are two things to really understand. First of all, composition does not equal structure. So if you do a MALDI analysis of your glycans and you get composition data, that is all it is. It's just telling you how many hexoses, how many hexnacs, how many fucoses, how many sialic acids. It's not telling you how they're linked together. It's not giving you any linkage information. It's not giving you any anomoricity. So you need to know that, because lots of the literature is really full of glycan analysis where they've put a structure there, but actually there's no evidence for that structure. That structure just represents one possible arrangement of the composition. And the other thing to be aware of is that one type of analysis is not enough. I mean, everyone who's a chemist here will know if you're going to look for copper, you can put your material in a flame and you can look at the colour, but that's not enough. You also have to have another analysis to confirm that you've actually got copper present. And sugar analysis is no different. You need orthogonal technologies, so two technologies that give different kinds of information in order to first assign a structure and then to confirm it. And you'll see a lot of things in the literature where they do not have orthogonal confirmation of the structure. So again, as glycoanalytics gets more sophisticated, you need to just be very critical of what you read in the literature. And when you decide on technologies, there are a number of things that are really important. Quantitation. If your method is not quantitative, you need to know that. Doesn't mean you can't use it, but you need to be aware. How quantitative is mass spectrometry? How quantitative is capillary electrophoresis? How quantitative is ion mobility? All these different technologies have different reliable quantitation. And how sensitive are they? What's their dynamic range? Can you see sugars that are present at 60% of the total sugars? And can you see things that are 0.01% of the total sugars? Because some technologies just, your 0.01% will just be down in the grass and you'll never see it. So how sensitive is it? How robust is it? If you do the same thing 20 times over, will you get the same result? Because it's very confusing if you've got a technology that's not reproducible. And also the speed. Well, the speed is really important, but not at the expense of getting rubbish data. So there's no point in having a very fast method if it's not reproducible, if it's not sensitive, if it's not giving you the kind of information you need. So you need to think, what's the most important thing about this analysis? Do I need something very quickly and I'm prepared to sacrifice the quantitative nature of the data, for example? Why am I really doing this analysis? Because every technology is useful. Every technology gives you a piece of information, but you need to know the capabilities of that technology and what its limitations are. And I think if you go away from this talk understanding this slide, then you'll be able to do it on your own, because these are the questions that you always need to ask. And we did try to help by writing this review in 2010, and it's pretty much still valid, really. We looked at all the technologies that were around at the time, and we tried to assess when you would use which technology in your glycoanalytics. So, as I say, understanding the real structure of the sugar requires you to know monosaccharide sequence, because you have to know the anomoricity, whether this linkage is going above the plane of the ring or whether it's going to be below the plane of the ring, and that gives you the alpha linkage or the beta linkage. This is a beta linkage because it's above the plane of the ring. And you also need to specify which hydroxyl group is actually taking part in the interaction. So here, this is, you start from the oxygen, this is 1, 2, 3, 4, 5, 6. So this is a 1 linkage, and it's linked to the carbon number 4 in this monosaccharide here. So you have to be able to specify whether it's bound to a 4 position or a 3 position, 2 position, or even a 6 position. And also you have to be able to specify the branching, because here, for example, you've got a 1,6 arm and you've got a 1,3 arm where it's branching at this mannose residue. This mannose residue has 2 other mannose residues attached to it. One's attached to the 6 arm and one's attached to the 3 arm. So that's very important to know if it's not symmetrical like this one, if there's an elongation here, so you've got some more residues like the lactosamine extension, you need to know whether it's on the 1,3 branch or on the 1,6 branch. And there are, of course, many reasons to do glycananalysis. This is the slide I showed yesterday. You may want to do fundamental research to understand the genetics that control IgG glycosylation, for example, in which case you'll definitely need a detailed glycananalysis. You might want to select your cell lines. You might have a whole lot of cell lines which are high producing. So when you select when you do your clonal selection, first of all you pull out cell lines that are high producing, and then you look for other features. And glycosylation is one of those. And it's because you want to select a cell line that has optimal glycosylation for your function. And you might also, here at this point, want to compare your glycosylation with an innovator drug. So you need a technology that's going to enable you to look at maybe 50, 100 different clones very quickly to get that kind of information. And also to determine safety and efficacy of a drug. All of this is part of quality by design. So the idea is that before you start doing your bioprocessing, you actually design the process to give you what you want, to make sure you don't have any alpha-gal residues, for example. So you might delete out the enzyme that puts on alpha-gal, or you might choose a cell line that doesn't put on alpha-gal in the first place. And then you come to production and scale up. And it's really important to get this right, because if you go into like even 150 litre scale up, you're going to waste an awful lot of money if you end up with tons of stuff that's got an antigenic epitope, and people get very annoyed with you because you waste a lot of money on something you should have known about before you started doing it. So this stage is really critical. And then you come to production scale up. So in this big tank, these are cells that were never meant to be in a big tank, right? They're probably Chinese hamster ovary cells. They are trying to do something, but they're certainly not being ovary. They're not part of an ovary anymore, but they're communicating with each other. They're an organism in some sense of the word. So understanding and thinking about what's going on in this cell culture, what's the pH, not just in one place, but all over. What's the mixing like? What the oxygen levels like? Is there a patch of hypoxia? Because hypoxia will certainly alter glycosylation as it does in tumour cell environments. And the media composition, what is the media, the right composition to get you the glycosylation you want? And very importantly, is there a lot of cell death? Because Octavia showed yesterday that if you have a lot of cell death, the enzymes that are released if you're making EPO, they can take the sialic acid off your EPO before you've even recovered it. So preventing cell death is another really important thing. And scale up, more than one company has come to grief in scaling up. So the people have scaled up and assumed that the glycosylation will stay the same. But it doesn't. It changes if you make a big scale up. So you have to you have to do it gradually, and you have to check you haven't got glycosylation changes as the batch gets bigger and bigger. And of course you need to monitor at line. Now at the moment people are developing sensors to be able to put into your processor, and they will circulate around and they will send out information about pH and temperature and that kind of thing, and you'll get kind of a three-dimensional picture of what's going in your bioprocessor, and that's really very neat. But there's nothing like that for sugars, and that's what we need to invent. But of course it's far more challenging than just having a sensor that will register pH and then send a signal to your mobile phone. You know, it's just not that simple with glycans. So at the moment we're still stuck with at-line monitoring, and you need to do this because sometimes you can actually troubleshoot. If you see that your mannose levels are getting very high, for example, it probably means your cells are exhausted. So you either need to slow down the process or you need to stop it and recover your glycans at that point, your protein at that point, because it's only going to get worse and you're going to get a lot of material that you don't want in your final product, and then you're going to have to remove it. So troubleshooting, if you can't change the glycosylation by putting in a different amount of glucose or feeding at a different time, if you can't troubleshoot, you might actually decide to stop the process. And you need to be able to do the analytics at the purification and formulation step. And sometimes you need to be able to analyze fractions in downstream processing. So, for example, 60% of erythropoietin is thrown away at the downstream processing stage because it has the wrong glycosylation. So you need all kinds of reasons to have glycan analysis at this point. When you come to product analysis, of course, now you're trying to satisfy the regulators in the first place to demonstrate that you have appropriate levels of critical features. If you're making biosims, you have to show that they're like the innovative or very similar to the innovator product. And then, of course, in the end, you're going to want to make batch releases. So proper analysis at this stage is really important. And testing function as well, because I was talking yesterday about these Fc gamma interactions. More and more people are asking, you already have to show that your IgG will do what you think it's going to do. And more they're going to be asking, can you show that it isn't doing anything else? So this is still in the research area, but it's important to understand that it's coming online. And then product stability, of course, you need, glycans are very stable. It's not usually a problem, but you do need to be able to test that your glycans are stable on your final product. And so the first part of the talk, I'm going to talk about IgG, then I'm going to talk about erythropoietin, and then I'm going to talk about etanercept, because those molecules increase in complexity of glycan analysis. So we'll just see how far we get. But please ask questions. So is everyone okay so far? Yeah? Right. So there are lots of FDA-approved antibodies, IgG1 to fusion proteins, IgG4, and so on. The vast majority of them are IgG1 subtype. So this is IgG1. It has this particular hinge, which is the most characteristic difference between the different subclasses of IgG. So you have to have a multifaceted approach, as I said, to do glycan analysis. And this is what everyone would like to be able to do for every glycoprotein. They would like to have this top-down approach. So they would like to be able to analyze the whole population of molecules at the protein level. So this is analyzing IgG as an intact glycoprotein. Now, you can do it, and I'll show you the data in a moment, but this is still quite difficult, and because IgG is so big. So if you do a Fab fragment or something, it's much easier. But many glycoproteins are not really, you can't really use this technology either because the molecules are too big or because like for erythropoietin, the complexity of the profile is so huge that you can't really hope to interpret it just with a 1D analytical method. So the next level down is to make the glycopeptides. So you cleave your protein with trypsin or chymotrypsin or with some protease that will give you the kind of peptides that you think you want to see. And then you analyze the glycopeptides. Now, at the moment, most glycopeptide analysis will only give you composition. So it will give you a structure like this, but there's no bonds, it's not telling you the anomерicity. This is just one arrangement of these glycans. And it will give you the site that those are attached to. So this is very helpful. It helps you to assign different structures by doing further analysis. And I'll show you these in a bit more detail in a minute. Then the next level down is to release the glycans to get composition. So again, you can do a quick mass spec and you can get structures like this, which are composition. They're not claiming any bonds. Although they may argue that from the pathways that we know, this really must be this structure, but that's not really proof. That's argument by analogy. And then there's the release glycans, which you analyze in detail, and this will actually give you structure. So this is a representation showing structure. So these are the monosaccharide residues. Here's the anomoricity, dotted lines or straight lines, and the angle, as I showed yesterday, defines the linkage. So the intact protein analysis. So this is the anti-HER2 antibody, and this is the mass spec that you get on an Orbitrap. If you go into this peak in more detail, you see it consists of this whole range of different masses. And if you deconvolute it, you can assign to each of these structures a mass which would be consistent with these different assignments. Now this is important because IgG has 2 glycans. Please, 2 glycans. You would be amazed how many reviews you read where they say IgG has 1 sugar. So it has 2 sugars, 1 on each heavy chain. And these heavy chains are identical. They're not mirror images. So if you just think about it for a minute, one of these sugars is coming from the front of the molecule. The other sugar is coming from the back of the molecule. And they do interact with each other, and they do interact with the protein surface. So it's really worth taking some time to understand the structure of IgG, because I'm constantly amazed how many people work with IgG day in, day out, but they really don't understand how the sugars fit in this CH2 region. And the reason that it becomes very important is that we know that modulating the glycosylation of IgG... Yeah?
Sorry to interrupt, but Dr. Royston Jeffries says that the molecule is symmetrical.
Yes.
And we have 2 oligosaccharides,
yes.
1 on each side.
Yeah.
If we calculate the number of structures that we can have in one IgG is like 600.
Yes, but the number you actually get is very small.
Exactly, that's the question.
Yes, it's very small, and this is what's called pairing. And in fact, Roy years ago, Roy did some very elegant experiments looking at the pairing of these 2 sugars. Because the big question is, if you have something that can bind those sugars, like the mannose binding lectin, for example, if you have 2 sugars here that both terminate in a ligand for the mannose binding lectin, like N-acetylglucosamine, can you actually get 2 domains of the mannose binding lectin to bind simultaneously? And so does it actually make a difference to the valency if you have 2 sugars with appetite, or is it only ever going to bind 1 anyway? So it doesn't matter if you only have 1, it will still bind. So if you just think about this for the interactions of IgG with all its receptors, this is really crucial information. And so even the Fc gamma receptor, if you have 2 IgG sugars, neither of which have core fucose, is that molecule going to bind more effectively to Fc gamma receptor than one that's only got 1 sugar without core fucose, or a molecule that has no core fucose at all? So understanding the true glycoform. So a glycoform is a single amino acid sequence and a single sugar at each of the glycosylation sites. That's what defines a glycoform. So if you look at one protein, one IgG molecule, what actually do you see? And just knowing the population of glycans doesn't give you that information, but this does. It really helps you to understand what this whole molecule looks like. So you can look here and you can see the most abundant IgG molecule has G0F and G1F. So it has 1 sugar which has no galactose and 1 sugar which has 1 galactose. In this population of anti-HER2 antibodies, that's the most common. So then you can start to think about this and think what this means for the interaction of HER2 of the anti-HER2 antibody with the receptors, because you have like more complete information. So the more we can now exploit these very high resolving mass spectrometers to get this kind of information about glycosylated structures, the better our analytics is. But this is still really quite early days, and this really has not been done very often. This is some work that we did in Singapore. And you can look at some glycopeptides, and you can also get, if you look at glycopeptides, you can get composition data. So you can run your sample, you can assign, if you cut it up with, if you cut it up with trypsin, what the peptides will be. You can, when you know what the glycan profile is of your whole material, you can take each of those glycans that you found, and you can add that mass onto each of the fragments, and then you can look to see if you have those fragments. So this is one fragment from IgG, this is the asparagine side. And you can, you know what your range of sugars are because you've already analysed them. So you can take the mass of this, and then you can add the mass of all of the sugars that you know could potentially be at that site, and then you can look for them. So if you're going to do composition using mass spectrometry, you always need to do a glycan analysis first. So you release your glycans, you do the glycan analysis, so you know what can be there, because you have to tell the computer which sugars to look for on your piece of peptide. So if you tell them everything, you'll see everything, because most of what you know, there are thousands of sugars that could potentially be here. So if you tell it to look for everything, in the graphs, you'll see everything. So you need to specify what sugars your MassLinks or whatever your program you're using is going to look for. So that's the way to do it. Release the glycans, analyze those, look at your peptide fragments, and then ask the computer to look for this peptide piece with all of the sugars that you've identified from your previous analysis. So that's top down, that's what we'd all like to do. At the moment, those things are more or less possible depending on the molecule you're looking at and the strength of your analytical technologies. But what we tried to do in my lab was to do something that was really simple, because when I started doing glycan analysis, it took one person 3 years to analyse the glycans on one glycoprotein. So it was a nightmare. So through various events, we tried to come up with something that really any well-founded lab could do, and you didn't have to be trained for 10 years in mass spectrometry to do it. So this is really what we suggest, that if you've never done it before, just try this, because it will work, and then you can get more sophisticated. So there are really several stages to glycan analysis. First of all, you've got to purify your protein. So that if that's IgG, you're probably going to pull it out on protein A. And then having done that, you have to bind your protein from your bioprocessor, bind it to the protein A, then you have to wash and elute it, buffer exchange, you have to get release your glycans probably from the protein A matrix. You then need to be able to prepare the glycans, to release them. So you do protein denaturation, you do alkylation, glycan release, filtration, cleanup. And then you can capture it on a solid support, you then wash again, and then you release the glycans. So this is about getting really pure material to begin with. Then you do fluorescent labeling, you do cleanup, and then you put it through some separations technology. So our first port of call is always UPLC, because it's just very straightforward. But obviously you can use other separation technologies, and then you have to integrate your data, and you have to quantify it, and you need some bioinformatics to help you assign the structures. So there are variations on this theme, which we publish many variations, so you might not want to capture it on a solid support, for example, but basically these are the steps that you need. Purify your glycoprotein, because if you don't, sample preparation is really critical. If you're purifying a glycoprotein, you don't get it pure, then you've got other glycoproteins in the mixture, you'll get skewed results. So that's very important. Releasing the glycans, making sure you've released them all, because if you don't use enough PNGAs-F, for example, if you dilute it out and out and out, in the end there'll be the fucosylated structures will not be released. So you need to make sure you use the right conditions for the pingase release. You then need to use the right conditions for the labelling, because if you don't use enough label, again, if you just keep diluting the label out, finally the fucosylated structures will fail to label in preference to something else. So it's absolutely crucial to use the right conditions, and it's very important to clean up, especially if you're going to go onto mass spectrometry, because if you don't clean up here, you probably won't get a mass spec signal, because the mass spec doesn't like detergents, it doesn't like salts, it doesn't like bits of old bits of protein that are hanging around. So this cleanup step is really vital. And so this would be the workflow that we use, but this is also part of the Waters workflow, because we work with Waters to make a workflow that would be implementable in labs that are regulated, and to have a lot of inbuilt computing to make this easier. But you don't need that. You can do that. You can do it all manually, just like we've always done. But you release your glycans. You then most likely want to do a wax separation. You want to separate the glycans by charge. You then want to take the whole pool of glycans, but also the wax separated fractions, and you want to run them through a UPLC, and you want to look for fluorescence. And then you might want to go on to pair that with mass spec. You take the UPLC data and you compare the peaks that you've got with the dextran ladder. So you'll do that tomorrow, I guess, later today. But you need to have a dextran standard to calibrate your column, and then you can give a glucose unit value to each of your components in your sample. And then you can interrogate the database, and you can say, my sample's got 4 peaks with these glucose unit values. What sugars could be at those glucose units? So this database has been compiled by us over at least 15 years. We've put numerous structures in there, and every time we see the same structure again, we take the glucose unit values, so we have very strong error bars on each of these glucose units. So you can go, it's open access, you can get it off the NIBIT website. You just take your glucose unit values, you look down the page of, in the database, and you can pick out manually if you want to. It's quite easy. You just a bit laborious, you pull out the preliminary assignments for each of your peaks. And so you get a number of hits, and then in each peak you'll probably find 2 or 3 structures that could be in that peak, or even more. And then the question is, how are you going to distinguish which of those preliminary structures is actually in your peak, or which of those preliminary structures are in your peak, because some peaks will contain several structures. So this is what it looks like. This is the LC, this is the dextran ladder. So this is the dextran hydrolysate. It's got glucose units, all different lengths. So it goes from 2 to 22 or something. So this is your calibration ladder. So this is your sample peaks. And so if you look up this one, you can read against here what its glucose unit value is. And there's mathematical programs to do this. And if you're using the Water software, it will do it automatically. But so once you've got your glucose unit value, you then search in the database. So you look for the glucose unit that you have. So this is on HPLC. These are the glucose units for these structures on UPLC. You look for the glucose unit value. It's got an error bar. So you take your experimental glucose unit. You decide yourself what's an acceptable error. So you then look within this chart to see which of these structures could be that glucose unit. Yeah.
Have you seen differences between the glucose units, the pure or royal?
Roy?
Calculated in the past? And
no.
Analysis you perform today?
They're rock steady. If you use the same conditions, the same columns, they're rock steady. And if you go on to the UPLC, which of course is new, that's technology with BEH columns that we developed with Waters because it's higher resolution. the glucose units will shift a bit. But I'll show you in a minute. A small shift in glucose units is not really a problem. This is so robust. But they will shift a bit, and if you use a different label, they will also shift. And the main differences are in the sialic acids. So the sialic acids will wander. So if you look at our papers, we actually don't ever quantify on sialic acids because we know their labor, we know they move around.
Okay. And depending on the nature or the principle of separation, for example, capillary electrophoresis and HPLC, is there any difference?
I'll show you some data. There is some difference, yes, but I'll show you how you can overcome that. But I'll just, if I can talk to the slide, it's easier if I show you the data. So this is an expansion of the NIBIT database. What Waters have done, we analysed a number of pharmaceutically interesting molecules with Waters, and they have what is a Waters database, which actually accesses this whole database, but it also it's very useful because if you can look up haptoglobin, for example, and it will give you the list of the structures that we found in haptoglobin or in erythropoietin, or so that there's just a help really. If you're analysing erythropoietin for the first time, at least it will tell you what we found in the particular erythropoietin that we looked at. And there are also, it's worth looking at this because there are lots of really nice features that we've built in, so it will automatically, if you ask it to, it will tell you what percentage are monoantennary, bi, tri, and tetra, and so on. So if you fiddle around in this program, we've had a lot of really good bioinformaticians who put some really nice functionality into it. So when you first begin your analysis, you have this set of peaks which represent the undigested glycans that you just released from your IgG, and you put a fluorescence label on. This is 2AB. And you run it out here, and then you look up in the database, and it will tell you which glycans could be in each of these peaks. So, for example, these structures could be in these peaks here. But then you use these enzymes to cleave back the glycans. So these are enzyme arrays. So the first one just has sialidase in, the next one has a galactosidase as well, this one has a fucosidase, and this one has 4 enzymes in. Now, the aim of these enzyme arrays is the last one, is to reduce all of these N-glycans to one single structure, to the trimanosyl core. So after you've incubated your released glycans with this set of enzymes, you shouldn't have any peaks left. And if you do, either they're slight residual peaks because the last enzyme, this one, is very hard to get to go to completion, or it means that you've got a structure there that is not reduced with these enzymes. For example, if you had manostructures here, they would still remain in their original position because there's no manosidase in these arrays. So this is really important fail-safe. It's not like mass spectrometry where you have to tell it what to look for. This is unbiased. It's going to look for what it finds, and then if there's anything left, it's telling you that whatever's left you have to look at further because it's not being reduced to the trimanosyl core. So if you had a phosphated sugar, for example, it wouldn't be reduced. So this is a basic array of enzymes which will tell you a lot of information, including you've got some strange things here that you hadn't anticipated. So as you can see, if you use these enzymes in turn, these peaks, this peak, for example, will first lose sialic acid, it'll move here, then it will lose galactose and move here, then it will lose fucose and move here, and then it will lose its N-acetylglucosamides and it will move here. So I just want to talk a few minutes about enzymes because these are really, really powerful tools. These enzymes are exoglycosidases. That means they will only take terminal sugar residues. And they are specific for particular monosaccharides bound in particular linkages. But if you use very high concentrations and you keep incubating for ages, they will display other specificities. So it's really important that just go through our papers, because I know our papers, but I'm sure other people as well, and make sure or go to the New England Biolabs with whom we've had now a 2-year collaboration cleaning up these enzymes. And make sure you use the conditions that they specify, right? Don't just go on incubating for days, because you'll get either contaminants that are in lots of enzymes that you buy will start to become important. They'll start to activate. And if you just keep very high concentrations as well, you will have other specificities. So this is the answer, is just to use what we have used for years and that work. So you do have two enzymes that cleave off sialic acid. Now, one of these is able to cleave all the different linkages, 2,3, 2,6, and 2,8. And it will, under the conditions that we use, it will cleave all of those. It's designed to cleave every sialic acid. If you want to know whether you have a 2,3 linked sugar sialic acid or a 2,6 linked, then you need to use this enzyme as well, because this enzyme only takes off 2,3, and if you really persist, it will take off 2,8, which are very rare anyway. So if you use this sialidase and with the nanny one, you will be able to find that some of the sugars are cleaved just with this one, and some are cleaved with, and all of them are cleaved with the ABS. So that way you remove your sialic acids, right? You then use these glucosidases. So BKF is the most commonly used one. This takes off alpha-1,6 and alpha-1,2 linked glycan. So it takes off this one, principally this core fucose, which is what you're thinking about when you're using IgG. Then there's this XMF. This enzyme takes off an alpha-1,2 linked fucose, and the AMF, the almond-milk glucosidase one, which takes off the 3 and the 4 linkages. So you can see the linkages from here. So you use fucosidases, and if you're using IgG, you probably only want to use this one. And so then you've got rid of all your fucose residues. So in the next array, you put in the sialidase and the fucosidase, but then you add a galactosidase. And there are two galactosidases. One takes off the 1,3 linkage preferentially, and one takes off the 1,4 linked galactose preferentially. So using these two enzymes, you can distinguish a 3 linkage here from a 4 linkage here. So as I say, these enzymes this one can take off 3 and 4 linkages, but this one only takes off 4. So that's how you know you've got the 4 linkage. And having got rid of the galactoses, you then use a glucosaminidase to take off these N-acetylglucosamine residues, and you also will eventually be able to take off this bisect, although that's often quite difficult to remove. So when you've done all that, then you end up with this trimanosyl core. So all of these enzymes have what's called an incremental value. So each glycan contributes a certain amount of glucose unit value to your total glucose unit. So if you know that the incremental value of a galactose is 0.8, for example, then you're looking in your enzyme digest, you're looking for a change of 0.8 glucose units, or if you have 2 galactoses, you're looking for a change of 1.6 glucose units. So they're poles apart on the glucose unit scale. You won't mistake a 0.8 for a 1.6. And because you know you've used the galactosidase, that's the only option. Either it loses 1 whole galactose or 2 whole galactoses. So this is why it's so robust. If the glucose unit's wandering a bit, when you do the enzyme digest, you'll immediately see the difference between 0.8 of the glucose unit and 1.6. So it's another reason why these enzymes are just so useful. And so, as I say, we had a collaboration with New England Biolab because we were really aware that lots of enzymes on the market are not very clean. We know that, so we always test our enzymes, and we're aware that they may have secondary activities. But if you're just coming into the field, it's like hugely confusing. So over the last couple of years, New England Biolabs have made all the major enzymes for N-glycan analysis recombinantly. That meant they had to grow an almond tree to make almond tree fucosidase. So this has been a huge project. But now they have all of these enzymes which are clean of other enzymes and also properly characterized. So they give you the activity. And so Obviously, enzyme activity will depreciate over time. So again, you need to understand what is meant by a unit of activity. So for NEB, it's the amount of enzyme that you need to cleave 95% of the terminal sialic acid from this structure in 5 minutes at 37 degrees. So that's, when you buy your enzymes, they should have this information there. Because if you had something lying around in a fridge for 2 years or something, you need to check what its activity is, or else just dump it and buy some new stuff. Because obviously any enzyme is going to lose activity over time. And also they also worked out the concentration that you need to remove these sugars properly. So they've done this with all the enzymes. So this is just some data from the alpha-2,3 neuraminidase. And the same with the galactosidase. Now this is really clean. This is SDS here. It's got a little bit of other stuff, but really very little. Now, if you just take some of the enzymes that you buy, you just run them on an SCS page, you will be surprised how much junk there is in some of these enzymes. So, they're not well characterized, and you can use them, but you need to be aware that there are hidden problems if you do. The purity and the checking that they work on these artificial substrates, but also on real oligosaccharides, because some of these artificial substrates, just PMP, sialic acid or something, it's not a test of how that enzyme is going to work on your biantennary structure. So, if you're going to look at these enzymes, perhaps you want to put a student to just have a look and see how these enzymes act on particular glycans and just understand the enzymology a bit. So that's about the glycans. So now I'm going to show you an analysis of Herceptin. So this is to find the critical features of Herceptin glycans and analysed by exoglycosidase array digestions in this slide. So this is the released glycan pool, nothing done to it, just these peaks here. They're assigned because we did the complete analysis and then put the assignment onto these peaks. But in the beginning, of course, you won't have those assignments. You'll just have preliminary assignments that you get from the glucose unit database. You then use the arterbacter-sializase, and you can see some of these peaks have moved. Lots of them have stayed where they are, so they didn't contain terminal sialic acid. But anything that moved has terminal sialic acid attached to it. And you can see how far it's moved. So you can see this one has moved a long way, and it's got 2 sialic acid residues. This one's moved much less, so it had 1 terminal sialic acid residue. And then if you then have the arterbacter-sializase in, you're essentially letting the BKF enzyme work on this profile, okay? So you're using an array. So it's just like you recovered this and then treated it with BKF. But you don't need to recover it, you just put both enzymes in together and you get the same, right? You see that? Because people often don't understand that that's what they're doing. Right? So you can relate these profiles to each other. So you look for peaks that have moved. So that one's moved, that one's moved, that one's moved. And that tells you that it contained outer arm fucose, and it's shifted by a number of glucose units that tell you how many fucose residues are there. So fucose is about 0.4 of a glucose unit. So either it's moved 0.4 of a glucose unit, or if you had some kind of glycan that had 2 core fucosidase residues with a plant or something, then it might shift 2. But in things that you're likely to deal with, there's only going to be 1 core link fucose. You then put in galactosidase, and again you can see, you just compare this profile with this profile, and you say, well, what did the galactosidase do to these glycans? Can only remove galactose, and they've all shifted. So this has shifted, this one's gone, and this little one's gone as well. And you can blow up this baseline. So the sensitivity is very good. So usually this is very crude. If you want to look at some of these smaller peaks, you just enlarge the baseline, you can see what's happening. And again, if you use the hexosaminidase, you can see that this peak is shifted because it's lost its N-acetylglucosamine residues, but you still have these peaks here. And these peaks as I was saying before, they're not digested by any of these enzymes, and actually they contain mannose. Okay? So you look at this last profile and you say, has everything gone back to the trimanosyl core? If it hasn't, then what do these glucose unit values correspond to in the database? And it will immediately come up with this mannose series, and then you do a digest which just